Welcome back to this next video in which we are discussing groups of order 12. Okay, so in the previous video we studied the alternating group on the set of 4 elements, which is an example of a group of order 12. What I now want to go back to is proving the main theorem of this video, namely that if you've got an arbitrary group of order 12, either the number of CELOF-free subgroups is equal to 1, i.e. you have a single normal CELOF-free subgroup, or your group is isomorphic to the alternating group on the set of 4 elements. Okay, so let's try and prove this now. So I will put the title Proof here. Okay, and remember we are dealing with now an arbitrary group once again of order 12. So we'll go back to calling our arbitrary group capital G. Okay, right. So, the first and obvious thing that we're going to apply is the third CELOF theorem to try and get some understanding of how many CELOF-free subgroups we're going to have in this group of order 12. So the third CELOF theorem gives us 2 pieces of information about the number of CELOF-free subgroups. Firstly, it tells us that the number of CELOF-free subgroups must divide what is left in the prime factorization of the order of the group once you've got rid of the highest power that 3 appears at 2 in that prime factorization. Now a reminder, 12 is just equal to 3 times 2 squared, so once you get rid of the highest power of 3, which is just 3 to the power of 1 in this case, what is left over is 2 squared, so this now says that the number of CELOF-free subgroups must divide 4. Okay, the second piece of information that the third CELOF theorem gives us is that the number of CELOF-free subgroups must be congruent to 1 modulo 3. Okay, now that means that it must be equal to 1 plus some multiple of 3, so I'll put 3 times k here, where k is some number greater than or equal to 0. It's an integer greater than or equal to 0. Now, this gives us only 2 possibilities. Okay, the 2 possibilities here are that n3 is equal to 1, in which case k is equal to 0, and of course then it does divide 4, so that satisfies both parts of the third CELOF theorem. And the only other possibility is that k is equal to 1, and therefore n3 is equal to 4, and that still satisfies both parts of the third CELOF theorem. Okay, but those are the only 2 options. If you make k larger so that it still satisfies the second part of the third CELOF theorem, then it's not going to satisfy this portion. It's no longer going to divide 4. Okay, so those really are the only options. n3 can equal 1 or n3 can equal 4. So proving our theorem then becomes equivalent to now showing that if our group of order 12 has 4 CELOF-free subgroups, then it is isomorphic to the alternating group on the set of 4 elements. Okay, now the first thing I want to show you is that the alternating group on the set of 4 elements actually does satisfy this. Okay, it does have 4 CELOF-free subgroups. Okay, so let me go back to what I drew earlier. Okay, so we saw that the alternating group on the set of 4 elements has a lot of these elements which are of the form a 3 cycle with a 1 cycle. Okay, so we saw that there were 8 of them in fact. Now, consider forming the subgroup which contains the identity and then one of these 3 cycles with a 1 cycle here, such as this one, and then itself squared, so it's pair, its partner if you like. Okay, and indeed we did go through these in partners. Okay, so consider forming the subgroup, for instance, that contains the identity, this one, and this one, which is this one squared. Okay, that will form you a subgroup of size 3, i.e. a CELOF-free subgroup inside of A4. Okay, and it's the same for all these other ones. So this pair here with the identity will form you a different CELOF-free subgroup. And the same for these 2 here. This pair with the identity will form another CELOF-free subgroup. And finally, this pair here with the identity will form the 4th and final CELOF-free subgroup. So indeed, the alternating group on the set of 4 elements does satisfy this condition that it has 4 distinct CELOF-free subgroups. Okay, right. What we now need to prove is that it's the only one. It's the only group of order 12 with 4 CELOF-free subgroups. Okay, and therefore any group of order 12 which does have 4 CELOF-free subgroups instead of 1 is isomorphic to the alternating group on the set of 4 elements. Okay, so let's just write this down then. Okay, so that's what we're aiming to prove now, that if G has 4 Seeloff-free subgroups, it's isomorphic to the alternating group on the set of 4 elements. Okay, so if I now write out explicitly then some notation, so we're just creating a bit of notation for now. So here's the set of Seeloff-free subgroups of G, and I'm now assuming that we have 4 of them. Okay, because of course the case where we have 1 is absolutely fine. Okay, that's part of the theorem, so this is fine. All I now need to prove is that if we have 4 of them, we are isomorphic to A4, and then we'll be done. Okay, so we're now assuming that we are in case B, where the number of Seeloff-free subgroups is indeed equal to 4. And I'm sorry, this is a little bit too high. I've altered the camera where the camera is, and now it's a little bit higher, it's a bit lower than it would usually be. I'll just have to keep watching it to make sure that it's still in view. Okay, right, so let's just devise some notation initially. So I would like some notation for my 4 Seeloff-free subgroups. Okay, so I'll call them capital H1, capital H2, capital H3, capital H4, because of course I'm now working in my more general group, capital G, of order 12, and I haven't yet proven that it is the alternating group on the set of 4 elements. Of course, the alternating group on the set of 4 elements would be an example for which we can use as G, where the number of Seeloff-free subgroups is equal to 4, but we haven't proven it's the only example, so I'm devising some more general notation here. So I'm going to call my 4 Seeloff-free subgroups capital H1, capital H2, capital H3, and capital H4. Okay, and the first thing to point out is that if you intersect any 2 of these together, so if I pick Hi and intersect it with Hj, where I is not equal to j, so I'll just add that, I is not equal to j, so you could pick I is equal to 1, j is equal to 3. If you intersect these 2 together, you will always get the trivial subgroup, okay, which I'll denote capital 1 as the intersection. And the reason is that whenever you intersect 2 subgroups together, we know that you end up with another subgroup, and it must be a subgroup of both of the things that you've intersected together. These things are Seeloff-free subgroups. They are subgroups of order 3, so we know instantly what they're isomorphic to. They're going to be isomorphic to the cyclic group on the set of 3 elements, and those cyclic groups on the set of 3 elements have a very simple subgroup structure. They only have the trivial subgroup and the improper subgroup. Okay, so either the intersection has to be the trivial subgroup or it has to be the improper subgroup for both of them. Okay, and that would mean that they were both identical, which contradicts I not being equal to j. So I can conclude that if I intersect 2 distinct elements of this set together, I will just get the trivial subgroup. Okay, right, so how are we going to use this information that we have these 4 Seeloff-free subgroups to actually arrive at the conclusion that G is isomorphic to the alternating group on the set of 4 elements? Okay, well, the way we're going to do it is we're going to devise a group action that is actually going to give us a huge amount of information. Okay, so I'm going to spend a little bit of time now making sure we're all familiar with this group action. Now, this is a group action that's used when we prove the Seeloff theorems. However, I will remind you of it here because it's so important to this proof. Okay, so what we're going to create then is we're going to create an action, a group action, by our group capital G on this set, of course. What else is the set going to be? Okay, so we will draw a group action composition table like this, and as usual we'll call our group action dot. Okay, so we'll put all of the elements of the set up here. We'll give every single element of the set a column. So each of these 4 Seeloff-free subgroups will get a column up here. Okay, like so. And I'll just colour in my group action composition table in red, like so. And then you'll give every single element of the group a row. So all 12 elements of the group, starting, let's say, with the identity element up here, will get a column. Okay, and then of course what you'll end up with is 12 times 4 entries in here, which is 48. Okay, so you'll end up with 48 little boxes in this great big table, which you will need to fill in, and they will define what any element of the group acting on any Seeloff-free subgroup here, any element of this set, is going to be. Okay, so how are we actually going to define the entries here? Well, the way we're going to define it is we're going to say that little g, which is an element of capital G, acting on a set Hi, is going to take it onto another set, capital HI, and it's just going to conjugate it. What else are we going to do? Of course, that's what we're going to do. Okay, we know that whenever we conjugate a CELOV free subgroup by any element of the group, you have to get another CELOV free subgroup back again. Okay, because whenever you conjugate a subgroup, you end up with another subgroup of the same size. Okay, all the subgroups of the same size are in this set. These are all the subgroups of size 3, and therefore whenever you conjugate one of them by an element of the group, you must get another one of them. So that's excellent. We are going to end up with all the answers in our composition table being back within the set. Okay, so it looks hopeful that this might be a group action. Let's just verify that it's a group action, because remember there are two axioms that a group action composition law must obey. Okay, axiom number 1 is compatibility with the composition law on the group. So for all little g1 and little g2 that you can possibly pick from the group capital G, and for all elements of the set that you can pick, so for all capital HI from the set of all CELOV free subgroups of G, it must be the case that if I act G1 on the result, so I'll put dot there, on the result of G2 acting on HI, that it is the same, you'll get overall the same subgroup back again as if you firstly compose G1 and G2 together using the group composition law and then act to the composite of them on HI. Okay, right, so this is axiom number 1 then, that a group action must obey compatibility with the group composition law. And this is very easy to prove, even though it looks quite a complicated statement. This is actually just saying that the group action respects the composition law when you do one of these elements. Well, remember what a group action really does. It ascribes to every single element of the group a permutation of this set here. Okay, so really what this is saying is that the composition of two elements of the group is consistent with the composition of the set permutations that they are being ascribed by the group action. Okay, so if you want to compose two of them together, you can either compose them together in the group, or you can take their permutations of this set that they represent and compose those two together. The answer's the same. That's what this is really saying. Okay, right. So how can we prove this? Well, we just apply the definition that we've made up here. So G2 acting on HI, what's that going to be? Well, it's going to be the G2 conjugate of HI. So we will conjugate HI by G2. We'll go through all the elements and conjugate them by G2, and we'll end up with another CELOV free subgroup. What we're then going to do is act G1 on that. Okay, so we're going to take the answer here, and I'll just underline it in red. We'll take this answer and then conjugate it by G1, but of course that's utterly equivalent to just going through all of these elements and then conjugating by G1. Okay, so because all the elements in here are just elements of HI conjugated by G2, it's going to be the same as now just conjugating by G1. Okay, like so. Okay, and clearly, because of associativity of composition in the group, really the brackets would be like this if we're doing it from the left-hand side, but because of associativity of composition in the group, we can turn this into G1 composed with G2, put brackets around like that, and the answer there, conjugating HI, because on this side we'll then have G2 inverse composed with G1 inverse. So because of associativity of the composition law in the group, we can do this. And of course, this is just the definition of G1 composed with G2 acting on HI. Okay, so truly, axiom number 1 does work. This is compatible with composition in the group. Okay, and then axiom number 2, what's lovely about group actions is that there's only 2 axioms. Okay, axiom number 2 is that the identity element must act on all of the elements of the set to give the same element back again. So for all HI is an element of the set of CELOV free subgroups in G, it must be the case that the identity acting on HI is just equal to that HI back again. Now, hopefully that's obvious to you because, of course, just by definition, this is just conjugate HI by the identity, and that will have absolutely no effect at all. Okay, so this row dedicated to the identity up here in our group action composition table, this is going to be really simple. I can now fill this in the identity acting on capital H1 will be capital H1, the identity acting on capital H2 will be capital H2, the identity acting on capital H3 will be capital H3, and the identity acting on capital H4 will be capital H4. And you can see here that the identity has been associated now with the identity permutation on this set. Okay, so indeed, this way of defining the entries in this composition table does obey the axioms of a group action. So what this is successfully going to do then is associate with every single element of the group a permutation of this set of 4 elements. Okay, this set of 4 CELOV-free subgroups here. Okay, and this association of permutations is going to be compatible with the composition law on the group, i.e., if you have 2 elements in the group, you can either compose them together in the group and then map them onto the permutation that that composition of the 2 is associated with of this set of 4 elements. Or you can firstly map each of those elements onto the permutation of the set of 4 elements that they are associated with and compose their permutations together as just composition of mappings. Okay, and the answer will be the same. Okay, so truly, you can think of the elements of the group as representing these set permutations of this set of 4 elements, and that is in fact how we're going to gain a huge amount of insight into this group, because look what I've done now. I have associated with each element of the group here a set permutation of a set of 4 elements. What are we trying to do? We are trying to prove that this group is isomorphic to the alternating group on the set of 4 elements, where we explicitly make the connection with the elements representing permutations of a set of 4 elements. Okay, so this is going very nicely. Okay, I've now been successfully able to associate with the elements of the group set permutations of a set of 4 elements, okay, in this way, through this group action. Now, before we actually finish this and do make the conclusion that you've probably leaped to in your head now, what I want to point out firstly is that the normalizer of any one of these subgroups, these CELOV-free subgroups, capital HI, is going to be equal to capital HI. Okay, so this bit is going to be important, but initially you won't see why I'm bothering to do this. Okay, so if you like, we'll have this as a little lemma that we can get from this group action, but it's not going to be the final conclusion that you're wanting me to make now, but we do need to do a little bit more before we can make that. Okay, so here comes a little lemma then. Okay, so the lemma is going to be that the normalizer of each one of these CELOV-free subgroups, so capital HI, is just equal to capital HI. Now, how can I do that? Well, I claim that I can conclude that from this group action. Okay, and let me show you how. So, we know that any group action allows us to split the set on which the group is acting down into orbits, and then we can apply the orbit stabilizer theorem, and that's how we're going to do this. So let's just think about the orbits that the set is going to be split into. Well, I claim that this set of 4 elements, I'll just draw out a little picture. So this can be the set of all CELOV-free subgroups in G here, and of course we know it contains 4 elements, so H1, H2, H3, H4. So we now want to think about what are the orbits then that this set is going to be split into by the group action. Well, the definition of an orbit is if you want to find out the orbit of a certain element, so let's ask about the element H1, what you have to ask is what are all of the elements in the set that capital H1 can be mapped onto by elements of the group acting on it. So you go through all of the elements of the group here, you ask what is that all of those elements of the group acting on H1. So you go down this column, look at all the entries, and then all of the entries that appear in this column, those are grouped together, and that subset is the orbit of H1. Now I claim that the orbit, there's only one, okay? The orbit is the entire set, and therefore indeed the group action is transitive. Transitive is a fancy word for a group action which has only one orbit, splits the set into a single big, large orbit here. And the reason it's going to be a transitive group action is because all of these free subgroups are going to be conjugate to one another. That's part of the Sylow second theorem. So all Sylow free subgroups are going to be conjugate to one another. Indeed, all Sylow subgroups of a certain pertaining to a certain prime are always going to be conjugate to one another. It's not just for free subgroups. Okay, so all of these must be conjugate to one another, and therefore, if we go down the elements of the group, there must be some elements of the group that you can use to get H1 to conjugate onto each one of these. So I must find H2 in this column, I must find H3 in this column somewhere, and I must find H4 in this column. So they all appear in just one great orbit, and it's the same for all the others. All the others' orbits will be the same as the orbit of capital H1, okay, because we know that the orbits form a well-defined partition from our study of the orbit stabilizer theorem long ago in this playlist on group theory. Okay, so indeed it's a transitive group action. There is this one orbit which consists of the entire set. Okay, now what we can do is apply the orbit stabilizer theorem, which says that the order of the group that is acting on the set is equal to the order of the orbit, which we now know, times the order of a stabilizer of an element. Okay, so we'll stick with H1 here, but we'll quickly generalize it. Okay, so the order of the group that is acting is 12. The order of the orbit is 4, and now what I want is the order of the stabilizer of a certain element. And I could do this for any element you like. The formula would still be exactly the same, and in fact, actually I will. I'll generalize it right away. So now what I can put in here is the order of the stabilizer of any one of these 4 elements. It'll be true for all 4 of them. So in fact, I'm getting 4 equations for the price of 1 here. Okay, now what is the stabilizer of an element? Well, the stabilizer of an element is going to be the subgroup of the group capital G, which consists of all the elements in capital G, which when they're used to conjugate a certain subgroup, keep it the same. Okay, and of course that's the definition of the normalizer. Okay, the normalizer of HI in G is just equal to all of the elements in capital G, which when they're used to conjugate capital HI, leave it unchanged, fix it. Okay, give us the answer capital HI. So I'll write this out explicitly somewhere. So the definition of the normalizer of HI in G is that it's the subgroup of capital G, and we know it does form a subgroup. It's all little g as an element of capital G, such that little g, when used to conjugate capital HI, gives as the answer capital HI, fixes this subgroup. Now note, it doesn't mean that it fixes every single element of the subgroup. Okay, it might move the elements of the subgroup around, but overall, the subgroup that HI is mapped onto by conjugation by G is itself. Okay, but as I say, it doesn't mean that it fixes every element inside there. That's a stronger concept known as the centralizer of the subgroup capital HI. Okay, and we don't want that. We don't need that for this group action. The stabilizer doesn't need to be centralizer elements. It just needs to be normalizer elements. Okay, so by the orbit stabilizer theorem, I can say that this equation is true for all of the HIs. So for H1, H2, H3, H4, this is true for all of them. Okay, and therefore I can say that the order of the normalizer of HI in G is equal to 3. Okay, now how from that can I then conclude that the normalizer of HI in G is just HI itself? Well, the reason is that all of the elements in the subgroup capital HI, when they are used to conjugate HI, will fix it. Okay, if I take an element of a subgroup, okay, so if I take a little h, which is in capital HI, then when I conjugate capital HI by little h, of course I get HI back again. Okay, so all of the elements of a subgroup will always be in the normalizer of that subgroup, but each of these subgroups is size 3. The normalizer is size 3, hence they must be equal to one another, and that's how I can conclude that the normalizer of HI in G is just equal to HI for each of these Sylow-free subgroups. Okay, now as I say, you might not see why this is important. We were going down a very logical path towards being able to prove that our group was isomorphic to the alternating group on the set of 4 elements, and you might think I've just gone on a wild tangent now, but this is going to be important for making the final conclusion. Okay, so we'll have a break here, and in the next video what we will do is make that final conclusion that our group capital G is indeed isomorphic to the alternating group on the set of 4 elements.